Conjugated visual predictive control. Visual servoing is a technique in which we utilize the feedback information provided with a visual sensor to control the motion of a robot. There are two classic visual servo control approaches, image-based visual servoing and position-based one. In IBVS, there is no need to the camera pose estimation or external calibration, and consequently, there is no need to the target's 3D model. But we may have the singularity problem, camera retreat or advanced problems, and local minima. On the other hand, in PBVS, although the system is globally asymptotic stable and we have direct control over the camera motion in the Cartesian space, but a precise model of the target is required and the controller is really sensitive to the camera calibration errors. In addition, the target may leave the camera's field of view. Generally, there are different constraint categories in visual servoing, such as visual, robot-related, control-related, and task-related constraints, which must be addressed in any successful application of visual servoing. So we decided to utilize the model predictive control method, which has the superior performance in constraint handling. On the other hand, to make the system robust in presence of the uncertainties and modeling error, the existing predictive controller has been embedded into the internal model control structure. Similar to other predictive control methods, conjugated visual predictive controller has four essential elements. The first one is the reference signals, which are the concatenated reference coordinates of the visual features and the final target pose expressed in the camera frame. The second one is a linear predictive model of the dynamic process as shown in the figure. The third element is the cost function, which should be minimized in order to obtain the optimal controls input. Here, the cost function is a weighted function of the norms of 2D and 3D errors. The weighting factor omega could be either constant and equal to 0.5 or time varying. And finally, we employ the sequential quadratic program to minimize the existing cost function in presence of available 2D and 3D or control constraints as demonstrated here. As it was mentioned before, one of the issues in the IBVS and also in its predictive equivalent IVPC is camera retreat or advanced problems. These issues emerge when there is a large amount of pure rotation around the optical axis. In Chomet conundrum, which is the 180-degree pure rotation around the optical axis, the control of a free-flying camera by IVPC will fail due to having unbounded retreat or advanced problems. These issues will be alleviated in CVPC by utilizing the combination of PVPC and IVPC. On the other hand, in PVPC, due to having no direct control over the 2D visual features, they may leave the camera's field of view. This issue will be resolved in CVPC by employing a weighted combination of IVPC and PVPC schemes and having control over the 2D visual features. As it was mentioned, the cost function is the weighted function of the norms of 2D and 3D errors. The weighting factor omega can be either constant or time varying. In the case of constant weighting factor, the omega is equal to 0.5 during the control procedure. On the other hand, in the case of time varying weighting factor, the weight of 2D and 3D costs will be changed based on their closeness to the penalty zones. The difference between camera trajectories in the procedure with constant and time varying omega has been demonstrated in this figure. On the other hand, the effects of tightening the 2D penalty zone have been shown in these three diagrams. To demonstrate the performance of the CVPC, a model of the 6th degree of freedom Puma 560 arm has been employed. As it was expected, by increasing the prediction horizon, both of the 2D and 3D trajectories became smoother, and the pressure on the robot's actuators became less, while the predefined constraints have been also met. Finally, to verify the robustness of the controller in presence of the system uncertainties and modeling errors, the camera measurements, the control inputs, and the camera intrinsic parameters are polluted by the following errors. As it's demonstrated, due to having the internal model control structure, the system was robust and the camera converged to its final destination successfully. Thank you for your attention.